So now you have been given, again, the same thing. You have been given the coins of some denominations, okay? And you have been given an integer n, okay? Now what you have to do is you have to find number of ways to make n. This question is different. In the last question, we were interested in finding what is the minimum number of coins to make n. Here we are interested in knowing then what are the different ways in which I can make n. Let's take a quick example. We have 1, 2, and 3, and n is 4. How many different ways are there? The question is that you have been given n, which denotes the amount which you have to make, and you have the same array that you had in the last question, and you have to tell me how many different ways are there in which I can make n rupees. Okay, let's take a look. I have got infinite supply of each of these coins. So what I can do is I can take 4 units of 1 rupee coins. So I can take 1, 1, 1, 1. That's it. Another way could have been I take 2 units of this and 1 unit of that. This sum is also 4. Another way could have been I take 2 units of this. And one more way could have been 1 unit of this and that. Is 112 different from 211? What do you think? Should both of them be considered same or different? They should be considered same, because here also the combination of coins is that you have 2 coins of 1 rupee and 1 coin of 2 rupee, and here also the situation is same. Just by jumbling up the order, you can't say that it is different. In order to be different, there has to be difference of some element. Like here I can say that it is missing out on ones and so on and on, right? So this approach that we are going to learn now is super powerful, has extensive application. See, think of it in this manner. This is your array, and this is the amount that you need to make. Let's talk about it in very basic terms. We want to make this much amount, 4 rupees. Let's write it here. Now what you can do is you can start your journey from the first element, or you can start your journey from the last element. It is up to you. So let's say I start my journey from the last element for now, which is at index number 2. See, this is your index 0, this is index 1, this is index 2. So let's say you start from index number 2. Now, tell me just one thing. When you are at this element, then how many choices do you have? Can I say I just have 2 choices? Either I can take this element once, or I can just leave it. Is it right to say that we just have 2 choices of this category? The answer is no. See, either you can leave it, or you can take it once, or you can take it twice, or you can take it thrice, because there are infinite supply. Okay, so the first choice that you can tell me is where you decide to leave this thing, where you decide to leave this element at index 2. So if you leave this thing, what will happen is, will your amount change? Your amount will not change. If you are leaving this, your amount will continue to be what it was. And now because you are leaving it, so it makes sense to move back. Moving back means coming from index 2 to index 1. So this is your leave transition. On the other hand, if you take it, if you decide to take this element, then what will be the remaining amount? The remaining amount will be 4 minus 3, which is 1. So let's write it. The remaining amount will be 1. But does it make sense to move back? Does it make sense to move back? The answer is no, it does not make sense to move back, because the moment you move back from here, you won't be able to take this thing again. So in this case, what we'll do is, whenever we take something, then we stay there. We stay there. So the index will not change. And why we are doing it? Because in the future, we might want to take it again. You see my point? So if you are leaving something, reduce your amount. Do not reduce your amount, because you're not taking it at all, and decrease your index. But if you're taking something, then reduce your amount, but do not change your index. So this is a very different kind of transition, but yeah, this is how it is. Now, I have a very simple problem for you. Let me define a function. Okay, here there are 2 items that you have. So the first item is an index, and the second item is remaining amount. Okay, this index denotes that the part of the array that I'm working in is from 0 to idx. And this remaining amount is just remaining amount. Now, f of idx tells me that in how many different ways, listen to it very, very carefully. F of idx comma remaining tells me that in how many different ways can I create this amount from this much array. So let me write it. In how many different ways are there to make remaining amount from the part of the array which is from 0 to idx. So you don't have to consider the denominations beyond idx because you left them. So you can take a quick example. What should be the value of f of 1 comma 4? So guys, if you see here, the meaning of f of 1 comma 4 is different ways to make 4 from the remaining array, which is from index 0 to 1, from here 0 to 1. From 0 to 1 you have got 1 comma 2. So you want to make 4 rupees from this much of array. How many different ways are there? Tell me. There are 3 different ways. First way is you take this 1 for 4 times, and second way is you take this 1 for 2 times and 2 for 1 time, and the final way is you take this 2 for 2 times. So that is the meaning of f of idx comma remaining amount. Okay, now can you tell me what will be the value of f of 2 comma 1? What does it mean? It means different ways to make 1 rupee, right, from the part of the array which is from 0 to 2. The part of the array which is from 0 to 2 is 1, 2, 3. So in how many different ways you can make 1 rupee from the given array? There is only one way, which is by picking that 1 coin. Okay, good. Now, if you have really understood the meaning of f of idx comma remaining, let me come to the point now. See, when you made this transition, then you rejected this element completely. When you rejected this element completely means all the combinations of coins that you will get over here will definitely not contain this element, which is array of 2, right? Because you left it and move ahead. So all the combinations here will be those which will not contain this item in it. And when you made this transition, then all the combinations in this will be that which will definitely contain the last element, which is array 2. So this is that combination which will definitely not contain this, and this is that combination which will definitely contain that, because this is for leave and that is for take. Now I can say that, hey, all the combinations that I get from here and all the combinations that I get from here will correspond to my overall answer. Why to overall answer? Because see, all the combinations that you get from here, f of 2 comma 1, what is f of 2 comma 1? F of 2 comma 1, we realized it is 1 only, because there is only one way to make 1 from this much part, which is take a 1 rupee coin. And if you concatenate your take transition to it, where you took this 3, then you can say, yeah, from here I am getting one way in which I can make 4 rupees from the entire array, correct? And from here, what was the value of f of 1 comma 4? It was 3. There were 3 different ways. So there were 3 different ways from here, and there was 1 different way from here. So total number of ways will be 3 plus 1, that is 4. Okay, so this way is that in which the last element is not included, but still the amount that you are making is equal to n. And this way is that in which the last element is included for sure, and the amount that you are making is again n. So whatever this function returns and this function returns, you add them up and that will be your eventual answer. Now, if you go ahead, you can just draw this diagram on and on. So again here, tell me, at every index, you have got 2 choices, leave or take, correct? So what is your current index? Current index is 1. At index 1, you have got a value 2, right? So if you leave this element, if you don't decide to take this element, will the remaining amount change? The remaining amount won't change, but you will move back, because in leave transition, our index always reduces. So you will come from index 1 to index 0. Okay, what will be the state in take transition? What do you do whenever you take an element? Whenever you take an element, then the remaining amount decreases and your index does not change. It stays the same. So if you take the element at index 1, which is 2, then the remaining amount will be 4 minus 2, which is 2. And you will stay at the same index, which is at index 1. Cool. This is how you can again move on. So again, you are at 0, 4. So again, there are two possibilities, which is of leave or take. So at index 0, you have got 1. So if you do not take this, your remaining amount stays the same, and you move on one index back, which is -1. And if you take the element at index 0, which is 1, then your remaining amount becomes 3. Okay, and you stay at the same place, which is 0. Now again, calls will keep getting made from here, so on and on and on. Now we need to think about termination condition. What to do in this scenario? Here the index became negative. The index became -1. What is the meaning of index becoming -1? No points. Very good. You're coming back. You're coming back. The moment your index became -1, that means there are no points that are left. So the physical meaning of this situation is that, hey, you don't have any coins with you. You have 0 denominations with you, and you want to make 4 rupees. Tell me, is there any way to make 4 rupees when we have no denominations with us? The answer is no. So if my index is negative, right? I'm just writing that rule. If my index became negative and the remaining amount is still positive, then there are no ways. So in this situation, we should return 0. This is very important. But now think and tell me, what if this remaining amount was 0? Somebody tells you that, hey, you don't have any denominations. Now tell me how many ways are there to make 0 rupees. You'd say only one way. Yes, only one way. And that one way is an empty set. You don't pick anything, an empty set. So if your I is negative and the remaining amount is 0, then there is only one way to make that. In fact, there is an interesting thing. You can see one thing for sure, that this thing is also reducing and this thing is also reducing. In all the calls that you are making, your index and remaining amount both are reducing only. It is never so happening that they are increasing. So use your brain and tell me one thing. Let's say your index is equals to 5 at any point of time. That means you will consider this much part of the array from 0 to 5. And your remaining amount is 0. So somebody tells you that, hey, in how many ways you can make 0 rupees if you have this much of denomination? What will be your answer? And how many different ways you can make 0 rupees? 0 is not the right to say. Your answer should be 1, because if you want to make 0 rupees, no matter what denomination you have or not have, you can always create an empty combination. You can always create an empty combination, and there is only one empty combination. So I can say, if my remaining amount is 0, I'll directly return 1. Why? Because no matter how many denominations I have, there is one and only one way to make 0 rupees, which is take empty combination. And I can take empty combination at any point of time without knowing what denominations I have. So that will be probably our first important termination condition. The moment remaining amount is 0, just return 1. There is only one way for that. Okay. And what to do if remaining amount is negative? You realize that certain times remaining amount can become negative also, right? Because think of it in this way. Let's say you wanted to make 4 rupees and this was 5. So if you would have taken it from 4, it would have become -1. So is there any way in which you can make a negative amount from positive denominations? The answer is a big no. So if the remaining amount is negative, just return 0. So these two termination conditions have to be there because my remaining amount is reducing. But another thing to be noted here is that your I, which is index, is also reducing. So you need to have one termination condition for your index also. If my index becomes negative, tell me, if my index becomes negative, and the way I have written my termination conditions is, this is my first, this is my second, this is my third. So you will come to this if only if these two conditions were false. If these two conditions were false, it automatically means that remaining amount must have been positive, isn't it? See, if an integer is neither 0 nor negative, that means that integer is positive. So if you come to this if condition, it means that your remaining amount is positive, but you are out of coins. Why you are out of coins? Because your I is negative. So in this situation, what to do? In this situation also you return 0 because you have nothing with you. You have empty denominations with you and you want to make a positive amount. There is no way you can make that. So these are the 3 different termination conditions that I would need to have. Let's talk about the code. What do you think? What is the dimension of this DP problem? Is it still one dimensional or is it kind of, it is 2 dimensional, right? Because you can see that there are 2 variables that are changing in all the different function calls. So let's say we have a function f and it returns an integer, which is total number of ways. And I need to pass here an index and remaining amount. Okay. Now, the first line of code, I can say if my remaining amount, this same thing can be copy pasted here. If the amount is 0, return 1. If amount is negative, return 0. And if I is negative, again return 0. Okay. Otherwise, what to do? Otherwise, if you are not at any of these termination conditions, it means you have to make the 2 calls. The first call is for leave and the second call is for take. So let's talk about it. See, you are currently at index I. So you are considering this area and you want to make this much amount. So if you are leaving this element, will your amount change? The answer is the amount won't change. So amount remains as it is if you are leaving it. But do you move back? Yes, we realize that whenever we leave, we move back. We move back. It's just the amount that does not change. So from I, you will move back to I minus 1. So the first call that you will make will be for this, and this corresponds to your leave transition. And then you need to have a take transition also. Can you tell me the variables for the take transition? Does the index change when you take something? Amount changes. Yeah. And by how much your amount changes? It's natural to say that if you're taking array I, then the remaining amount will be amount minus array I. So why don't you write that? So the remaining amount will be amount minus array I. And your index stays the same. That's it. Return this thing. This is for your take transition. The code is over. That's it. Again, a classical recursion code which has certain base cases and one recurrence relation. Do you feel that again here there can be repeated subproblems, overlapping subproblems? So it will definitely have overlapping subproblems again. For that, you will have to take a particular input. So let's say you have 1, 2, 4, and you have n equals to 10. How many of you can at least create a tree diagram for this? The way I have created here, can you create for this input? So please go back and create it. When you create, you will see that a particular problem which will repeat will be 1,6. So the point of me asking you to do this exercise is to convince yourself that overlapping subproblems will be there. So what to do if overlapping subproblems are there? How to tackle that? Memoization. So let's create a memoization array. Now think and say, what kind of memoization array will you need? 1D, 2D, 3D, which kind? 2-dimensional array, because it's a 2-dimensional problem. Now the next question is, what should be the size of it? What should be the dimension of this 2D array? See, at first dimension, you will have index I. Index, from where to where index varies? Index will vary from 0 to m-1, where m is the size of our input array. So the first dimension will be of size m. And the second dimension is for amount. What is the maximum value of amount? It is n. And then over the function call, it goes on reducing. So you need a m cross n array, and you can initialize it to -1 something. And then you can write your memoization logic. So the first line of code you will have over here is memoization check. You will see if mem of I amount is not equals to -1, that means it is solved, so you can return this thing. Otherwise, you will make the two calls, you will add, and you will store this result in mem, and then you will return that mem. Memoization part is very easy. So the real DP is memoization only. Okay. So DP is not tough. What is tough is your understanding of recursion. So that's the reason at Renaissance dashboard, if you take a look, we have given a lot of weightage to recursion and backtracking. And then you learn a lot of topics which are based on that, like trees, become superstar in recursion, and then only move on to something like DP. Do you see here that because the dimension of problem is high, so the space complexity is also high? I'll not talk about the case where n is 10 power 9 here, because in order to solve that, there are different ways to do that. So there you have to first look at the nature of input and figure out if the matrix could be sparse or not. And another way that you use to solve such problems is that is called as coordinate compression. So again, like that is not something which we'll venture into right now, but you can explore it if you're interested.